In this video, we have the goal of understanding the homogeneity property. So we're going to start with exploring and observing. What I'm asking you to do is to type in the y equals part of your calculator, and so this would be making y1 equal to the 4x squared and y2 equal to 4x. Then we're going to set up our table to start at 0 and change by 3 so that we get this list of values. And rather than walking you through all of that in your calculator, I am just going to fill these in. So this first function, our y1 function, I got a value here of 36. Next up, 144. Then 324. And finally, 576. For the second function in my y2 on my calculator, I had values of 12, 24, 36, and 48. Now, what we're going to do is go back through these and look at the relationship. So all of the relationships here in the factor for x column. So in this column, I say blank times, and they all are compared to the x sub 1. So my x sub 1 value is this 3, my first x value. Well, as I look at 6, my second one, it is 2 times the x sub 1. And I could figure that out if I couldn't do it in my head by just taking 6 and dividing it by 3. So I look at the next one, which is 9. How does that relate back to x sub 1? Well, 9 divided by 3 is 3, so it is 3 times bigger. And the final one, 12, well, if I take 12 divided by 3, that is 4 times as large as the original. Now, we're going to do the same thing for the y value. So we're looking at the factor for y. So the first y value is the 36, so that's our y1, and that's what we're always comparing to. So to fill in this first blank, I want to know 144, how many times bigger? So I'm going to take 144 and divide it by 36. And that gives me 4. So 4 times bigger. Now we will circle back to that, so I left some room there, but 4 times bigger. So the next one, I'm going to take my 324 divided by 36. And on my calculator, that gave me 9. So this is 9 times bigger. And then the final one, I took the 576, divided it by the original 36, and that gave me 16. So this one is 16 times 2. Now we're going to do the exact same thing for our linear function, which is the second one here. So first off, factors for x, well, the x numbers are the same. So this is 2, 3, and 4 times the original. Factors for y, well, our y1 is this original 12. And so 24 divided by 12 gives me 2. And the next one would be 36 divided by 12. And that gives me 3. And the final one, 48 divided by 12, and that gives me 4. So the question at the bottom is, how do power functions grow differently than linear functions? So the two functions that we're looking at, the first one is a power function, and that is because it has this exponent or power of 2. And the second one is a linear function, and that would fit the y equals mx plus b model. The plus b part here is 0, and so it's a very simple linear function. Well, with the linear, what I notice is that the factors for x are exactly the same as the factors for y. When I look at the power function, though, on the left-hand side of my screen, the factors for x are related to the factors of y, but they don't match. So when I look at the factors for x, 2, 3, 4, and I look at the factors for y, 4, 9, and 16, what I noticed is that 4 would be 2 squared. And 9 would be 3 squared. And 16 would be 4 squared. And so what I see here is that the base, the 2, 3, and 4, are the same for the x and the y. The exponent on them, which is always 2, matches the exponent up here in my power function. So my power function had exponent of 2, and when I looked at how x changed compared to how y changed, I see that it's always changing with that exponent of 2. So I want to try to put some of that in words as to how these are changing. So these are the words I came up with, but you might want to describe it differently. So for linear, which our example was the 4x equation, the factors for x and y are the same. And then when I have for power functions, so when I have power functions, and the example that we had here was 4x squared, what I found is that the factor for y is the factor for x to the k power and so in this case, that k power for this example only was the second power. But if I would generalize it, that k is representing whatever known exponent is given to you in the power function. So here, they were the same factors as x, but to the second power. And in general, they're going to be the same factors for x, but to whatever power is in your power function. So we're going to look at this a little bit more, a couple different perspectives. So here I have 2 squares. And the first one, the side length is 4 blocks. So whatever these blocks are, 4 blocks. And so if I find the area of this first one, I would take 4 times 4. So area equals 4 times 4, which is 16. On the second one, the side length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this side length is 12, which is 3 times bigger or larger than the little guy, because 4 times 3 is 12. Now, I don't want to count this all up, but I know 12 by 12, so the area for this one would be 144. Well, that's more than 3 times 16. 16 times 3 would be 48, but the factor is much bigger. So if I take 144 divided by 16, let's do that on my calculator, and see that it's 9. So the area to get from the little one to the big one I would take times 9. But the side, to go from the little one to the big one, I would take times 3. Well, I also know that area for a square is the length of a side squared. So I see that exponent is 2, and I see that 9 is really 3 squared. And so the factor for that input, the side length x, to the exponent for this problem gives us the increase in area for this problem. That's that homogeneity property. So one thing is just changing by a factor of, factors that word for something you're going to multiply by, so factor of 3. And then the other thing changes by that factor to whatever the exponent is. So let's look at another one. So here, the first thing is the radius is twice as much, or double. And so I see the radius on the first balloon, and it's just written here as r. And then I see the radius on the second balloon, and it's twice as long, 2r. The diameter is going to end up being twice as long. So the diameter is if we go the whole way across. So that's the diameter. So if I go the whole way across the first balloon versus the whole way across the second balloon, the second one, once I doubled the radius, is going to be double the diameter. But now when I talk about the surface area, which is like how much latex is making the balloon, that surface area is 4 times larger. Well, why does that happen? Well, because when I look at this formula right here, there's an exponent of squared. So if I double the radius, that would be 2r, and I would square that, and so then it's 4 times as long, because I can see the 2 squared in there would give me 4. But if I think of the volume, which is like how much air is in this balloon, it's actually 8 times larger. Well, how does that work? Well, I look at the exponent. The exponent is 3. I'm doubling the radius, so I would put 2r in there, put exponent of 3, and that's going to become 8 times as long. And so every time, whatever factor we use up here, this twice or double, is that factor that we have for the input. And then to figure out how that will impact the volume, the surface area, the diameter, we use the exponent in the formula. So let's talk about the actual formula itself. So this is the power function formula. And we want to talk about the different parts of this formula. So y over here is our output variable. And then, similarly, x is our input variable. But we do have some extra for x. We have something called a domain restriction. And so we limit the domain to the positive numbers. So our x has to be greater than 0. It doesn't even include equal to, just greater than. So we've limited the domain to positive. All right, the C on the front. The C also has some limitations. So this is a positive constant. So that's a limitation. It can't be 0, it can't be negative. And it equals f of 1. So that function notation has always been a little uncomfortable for us. So what that's saying, it equals the y value when x is 1. And then we have this k, and k is a known exponent. So I always think of k for known exponent. So you have to know what the exponent is. It cannot be a variable. If it's a variable, that would switch it to being an exponential function. So it has to known, and it does not have any limitations, so it could be positive or negative. So that is what our power functions look like. That's our details on it. And then our key property with power functions is this homogeneity property. So if the input is multiplied by a factor, then the output, which is the y variable, will be multiplied by that factor to the k power. So that's what we saw in all the examples. If the x was multiplied by something, then we took that same factor and used the exponent to figure out how y would be changing.